SEMM 2313, and now we will go for tutorial for flow in pipe. So this is question 1. The diagram shows a flow in a smooth pipe controlled by air pressure P1 in a tank. Calculate the pressure P1 required for the water to flow at a rate of 60 meter cube per hour. Take the bending coefficient as 0.4, the density of water as 998 kg per meter cube, and the viscosity of water as 1.003 times 10 to the power of minus 3 kg per meter second. So in this situation, we have a tank here, and this tank is pressurized with a certain amount of pressure. So, and then because it is pressurizing, so it could push water here to travel into this pipe and then to move out at this outlet. So according to the question here, we have a bending here, so 1 and 2. So and then the pipe has a similar diameter, which is we have a similar diameter which is diameter is equal to 5 centimeter, and the length of the pipe is 60 meters times 80 meters plus 60 meter plus 80 meter plus 30 meter. So we could conclude our question here as this one. So to answer this question, what you need to do is you need to evaluate the diagram first. So first, we need to identify the major loss and the minor loss. So for example, we have this one. So we assume that the streamline or the Bernoulli equation is actually can be calculated from this point until this point. So this is point number 1 and this is point number 2 for our Bernoulli equation. So and then according to this diagram, we know that at inlet here, so we have inlet friction coefficient or inlet coefficient, which is K is equal 0.5, and the outlet here is K equal to 1.0. And then we have a bending here, so it is given that the K is 0.4, and another bending here will give us minor losses with K equals 0.4. So and then water will travel from this inside this pipe, so and then finally it will flow out here. So while traveling inside this pipe, they will face resistance according to the roughness of the pipe and so on. So means that we need to calculate the major loss here. So because it only has one diameter, so we could assume that all this length can be calculated in one equation. So the total length here is 170 meters. And then we develop Bernoulli equation. So we have the energy at inlet is here. So and then this is the Bernoulli equation at point 2. So we add with major losses and minor losses. So let's say we calculate part by part. So we calculate minor loss first. So for minor loss, the equation is K V square over 2G. So and then from the diagram, we can understand that because the diameter is constant, it's always the same, so the velocity is remain unchanged at any section. So we could calculate it in one calculation like this. So where the 0.5 here is the coefficient for inlet, and 1 here is the coefficient for outlet. So we have 4 bending here, so we write 0.4 2 times. So and then from the flow rate and and diameter, we could calculate the value of velocity, which is equal to 8.49 meter per second. So, and then we could calculate total minor loss here, which is equal to 8.45 meters. So, and then we need to calculate the major loss. So the major loss, first you need to determine the Reynolds number, because we have equation for laminar and we have another method to find the value of F for turbulent flow. So this is the equation of Reynolds number, rho Vd over mu, and then we substitute with the value here, so we could get 4.2 times 10 to the power of 5. So means that it is more than 4,000. We could assume that the flow is turbulent. So if the volume is turbulent, the flow is turbulent, so we need to get the friction coefficient, the friction factor from the Moody chart. So, and then about the Moody chart here, so according to the question here, you could see that there is no data for roughness. So means that we cannot calculate the value of E over D or epsilon over D, because the diameter is there, but so this is the value of diameter, but the value of roughness here is not given. However, from the question, we know that the condition of the pipe is a smooth pipe. So, and then this is actually the biggest hint to evaluate the friction factor of this system. Because if you see the Moody chart here, so you will find that there is one line, the lowest line here is written as smooth pipe. So means that every time when you have problems telling about the smooth pipe, so you need to refer to this line, because this line is referred to the smooth pipe, for example the PVC or the glass tube. Okay, because the roughness can measure, but the value is very low, and it is not the line is actually around it will lays around this area. So that's why previous researcher they write this line as smooth pipe. So, and then according to the value of 4.2 times 10 to the power of 5, so we could mark the 4.2, which is here. So, and then it intersect with this smooth pipe line. So, and then if we bring it to the left, so it will give us this range. So it is between 0.010 to 0.015, but you could calculate 1, 2 and 3, so it is around, so means that the answer is as shown, so it is 0.0135. So, and then we write our Bernoulli equation. So this is the equation for inlet. So this is equation for outlet. So we have major loss and we have a minor loss here. So we substitute all the value. So we could find that the P1 is equal to 1.675 megapascal.